Whoop. Let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and I thank you for this class and this time we have left. We just pray that we would finish the semester well, Lord. In your name I pray, Lord Jesus. Amen. All right, so do you guys have any particular questions about anything? I mean, we can talk about the thing I just gave back to you guys, right? Give me a second here. I don't have like a standalone solution. I've got a few different things that are kind of put together. So I need to find if I can find it. Well, all right. All right, apparently a good number of the problems on your boss fight 1 previously appeared as Team Mission 3, which is something I was doing in 24. Come on. I will not miss this room, guys. It obviously has got something against me. All right. All right, so let's see here. So like, I'll try not to belabor these, but here was like problem 42. We had, y prime plus x squared y prime plus 2xy, and usual song and dance, plug it in. It gives you these recurrence relations. And after a bit, I found my way to a solution that looks something like this. Now, this might be able to, I suppose it's plausible that you could factor something out, maybe. I don't think so for this one, but so that's what I got. So that's that problem. I think this was problem 1 for you guys, maybe. I think this was your problem 2. Find the first 4 non-zero terms in the power series solution about 0 for this initial value problem. So, like, start with Taylor's theorem, and if we're smart about it, we'll put in that y of 0 is 1 and y prime of 0 is 0. That halves our work going forward, right? Because we don't even have to worry about the linear term. It's gone, right? It's gone. And so y prime, then you plug it back into the differential equation. Of course, here we need to expand sine and such as their power series. And so do that. Sine is x minus 1/6 x cubed and so forth. And there's my y prime, and x minus 1. I got to multiply this thing, right? So now when I'm faced with a problem like this, I don't actually multiply it all out in one big step, because that's just not a good use of time, and it's not helpful. Like, it's much smarter to just say, okay, I'm looking at the constant coefficient of this equation. I don't need to actually multiply it out. I need to think about how I would multiply it out and collect those terms. Focus all of my mental energy just on that, and that's what I do. So like constants, I'm like, okay, where are constants? Well, there's this 2c1. Anything else? Nothing. And here, that's got an x. There's no constant in this. There's that x. Lowest order could possibly be is x. In fact, it's actually x squared is the lowest order here, right? And here, your only hope is this minus 1 times stuff. So lo and behold, the only constant term is minus 1. So there you go, C2 is a half, just from looking at the constants. And then linear terms, x, the only way you get an x, of course, sitting right there waiting for us. And then here, there is no x term in that. And here, I can do x times 1. That gets me an x. And this could give me an x if there was an x over here, but there's not. So there's just the 2 terms with x, which gives me 6 to C3. And I think at that point, I'm actually already done, because I only said the 3rd order in your problem, right? Didn't I? First 4. I'm sorry. So one more step. I got to look at the x squared term, and that reveals to me that my C2 is minus 1/24. All right. So you guys can do these problems. You just have to be careful and take it one step at a time. Like, everybody is capable of doing these. They're not that hard. Like, the algorithm is literally assume a power series solution and plug it in. That is the whole calculational technique, pretty much. All right, fine. You got me. We do also need to know the power series expansions for sine, cosine functions that you were supposed to know the power series of from Calculus 2. Some of you are more rusty on that than others, but it's something that you could recover or learn. All right, anyway. I don't think this was on your... This was not. We didn't do this. So like we already did this earlier in the course, right? So that's not part of your math, your boss fight. So we skip over here to problem 46, I think, was the next one you guys had, right? Right? This is problem like 3 for you, maybe? Is that right? I think I still have some up here. Why don't I use them? Right? Duh. Yeah, I guess... Yeah, this is problem. So this is find the solution. Oh, it's a third order. And this is almost the same problem. The difference being, of course, we've got cosine x instead of x minus 1, right? But the process is the same. So let me just get to the answer here. We do have other things to do today. So that was... Now this one here, of course, we have 2 arbitrary constants in the answer. Why? Because the initial conditions were not given, right? So we expect 2 arbitrary constants in our general solution, and we do have those. And to get the third order, it suffices to take quadratic order for this piece, because the next non-trivial term is quartic. And of course, that's the third order. It's kind of just in your face right there. Okay, so, yeah. This one here, complete power series solution of y prime prime equal to xy. All right, so I differentiate the general formula, set it equal, look for my recurrence relation, and I quickly figured out that, was I given initial conditions here? No. Okay, so this one's, we're expecting 2 constants now. So if you look at the differential equation, you can see from that there's no constants in here, there's no constants in there, so that means that 2a2 has to be equal to 0, right? Well, that's good news, because there's like a connection between k plus 2 and k minus 1, so there's like a threefold, a triplicity, if you will, to the recurrence relation, and so like 2 of those are non-trivial and they're interlinked, and then the ones that are related to a sub 2, well, those are just all 0, so that's why we have ultimately 2 constants. And here's what they look like in terms of a sub 0 and a sub 1. Yay. All right, so ugly, but there you go. And, you know, it may be possible to reformulate these in terms of factorial, and this was just kind of clunky and not great that I had to write x out separately, but, you know, I'd rather have an ugly formula which is correct than not have a formula. So, there it is. You probably could improve on my answers here, okay? Yeah. Mm-hmm.
Why did you peel off the j equals 0 here?
Because my analysis was based on the assumption that j was greater than or equal to 1.
Okay.
So because of that, and then I started these sums at 1, I wasn't sure, and I just didn't want to think about it, and it's probably not true, that if I plug j equal to 0 into this, like j equal to 0 and this doesn't work,
Yep.
right? Because, oopsies. And over there, j equal to 0 has got trouble. And yet, j equals to 0 means something in a sense, right? I just have to go back to base principles. That's just the first step in the whole story, which is a sub 0 times x to the 0 power and a sub 1 times x to the 1 power. So that's part of the solution. It's just not part of this story, right? So that's why I had a separate formula for those. That may be insurmountable. There may be no way to rewrite this formula so that it folds in 0. I don't know. It's just I didn't come to it, and I didn't, like I said, this is better than no answer, but it may not be the best answer. So if you found a better answer which folds 0 into it and you feel like the grader counted you wrong, by all means tell me after class, all right? Because the person who graded this is not as good at differential equations as some of you. But they could grade it, so I was happy. Anyway, that said, if you feel like you've gotten points taken off where they shouldn't have been, come talk to me, right? You can have those points back probably. Frobenius solution is what it is. Again, this time we have to add that mysterious plus r, and that gets dealt with by the initial equation, which is down here. It ends up being 0 or a half in this one. And then, as usual, we have to face the recurrence relations. And after a bit of suffering, I came to these lovely formulas, which, of course, you could write in terms of like a summation notation, I suppose. I just wrote it this way because I thought it would be helpful to see it that way, I guess. But let's see here. Where are we? That was problem 5, and then problem 6. Let's see if I think that's next here. So you guys look at this. Now this is like a good test question, right? Like up till now, these problems. I mean, okay. So I might ask a I'm pretty much never put Frobenius method on the in part of the test. What do I? Well, anyway, let me shut up. But this would make it like a decent question on any one of the final exams I ever ask in this class, because this is not a hard thing to understand. Basically, what you're looking for is, where are the singular points? And so essentially, if the coefficient function of y prime prime is 0, that's going to be a singular point, right? So, I mean, to put it in the standard form we looked at in class, I'd have to divide the whole expression by x squared plus 4, right, to get to the starting point of our discussion in class about what a singular point is. And so, of course, we're going to have like plus or minus 2i for the coefficient of y prime prime, and pretty much, obviously, x equals to 4 is a problem, right? So we have 3 singular points, plus or minus 2i and 4. All right. Sorry. Aw, man. I'm not sure what happened there. Well, anyway, I'm talking about this to you guys now, so here we go. Is this one the one I gave you? I don't think there's anything wrong with the one that I gave you. It's just I'm not sure why I changed that to a 3 rather than a 4. Maybe it's just that I already had this written out when I scanned this thing. I don't know. I don't think it's anything terribly deep. I'm just being lazy. All right. So anyway, the point of this is, the question was, we're centered the solution at 1, right? That's important. So we have to think about relative to 1, right? Here's my singularities, and this is a slightly different problem than yours, right? So, I mean, we can figure out from this. Like the difference here with yours is what? Yours has got instead of having this here, it's got what? It's 4, right? So anyway, clearly this distance is 3, and this distance is square root of 5. So these would be the closest ones for you guys. So the answer should be like 1 minus the square root of 5 to 1 plus the square root of 5. That would be the correct open interval of convergence there. Let's see here. I guess I just don't have a solution to show you for the first 3 terms. Annoyingly. Oh, wait a minute. Well, fine. Here's the first 3. So here's the first 3 terms. 4 are related, but oh man, I really should have changed this. I wish I had changed that 1 over x minus 4 to 1 over x minus 3 right there. Sorry about this, you guys. Well, if you lost points on this part, you're almost certainly justified in getting your points back. So just tell me at the end of class and we'll add them back, okay? Does that seem fair? Because I'm pretty sure the grader would just have gone off that answer and not noticed that it's the answer to a different problem. So if you got points wrong, points off there, probably you deserve them back. Any questions? Nobody? Right. I have something I wanted to show you guys. This is actually something Dr. Skambordis wrote a few years ago, and he gave me a copy, and I thought it would be useful for us to just spend like 5 minutes looking at it, because it's kind of, I think, instructive. And so this is just a derivation of the wave equation. Very simple. What he does is he looks at the string, which is stretched between 0 and L, and here's kind of like a schematic picture of it. And as he says, the string is distorted at time 0 and released and allowed to vibrate, right? And what he does is he analyzes the forces that are on two close by points on the string, which he's called P and Q, right? This is deflected angle beta off the horizontal, and this is angle alpha off the horizontal. So he's analyzing the relation of these 2 points nearby in terms of the angles of the tangents of the string to those points. He says the problem is to find the vibrations of the string, that is to find its deflection, y of xt at any point x, anytime t positive. And he says we make the following assumptions. So we were always making these assumptions with the wave equation. And so if you're trying to analyze waves on a string, which we weren't following these assumptions, then the mathematics we studied this semester would not be relevant, right? And so there are some assumptions. One of the assumptions is that the mass per unit length is constant. It's a homogeneous string, right? If you had a lumpy string, you would need a much more complicated partial differential equation to analyze the waves on such a string. It's perfectly elastic. It does not resist bending, all right? So that's another assumption. The tension T is large, and we may ignore gravitational force on the string. So it's mostly, the motion is primarily about the string pulling on itself. It's not about gravity tugging it down, all right? That's probably the most unphysical assumption of these for a lot of actual string waves on strings that you've observed, right? Like a hula hoop or something. Like, does gravity matter to, like, not hula hoop, listen to me, with the people with the ropes and the jumping? What's that called? Jump rope, yeah. That's what they call it. What do you know? Glad I got you guys here. Otherwise, I'd just be like, what's that called? It's got a rope. It's got jumping. But what do you call it when you put it together? Like, I don't know. So, welcome to my world. And I teach 2 other classes after this where I'm dumber. Yes?
Have you seen those videos where people will like whip a really heavy chain on the ground and like the wave will travel and then it'll snap back towards them?
Probably at some point, yeah.
Have you ever thought about going into that wave equation?
Oh, like the wave equation on a heavy chain?
Like where gravity is
Yeah, I don't.
worse?
I mean, there is a problem earlier on where you can study the motion of a constant density chain, like a cable that falls off a table. And of course, the more that it falls, the more that's pulling on the cable that's already on the table. And the mathematics of that one actually involves the weird integrating factor stuff I don't cover. So like weighted chain problems are nasty, even the most simple ones. That sounds like a problem for Dr. Budares, because he's like a physicist and stuff. But no, that would be, there's some general principles we could probably extract from our study of the wave equation, but like,
A little bit beyond the scope.
yeah, probably. Well, for me at the moment anyway, but maybe not you guys. I mean, you could just numerically model it, right? And then I should just ask AI what happens. Then we have to trust AI, right? I mean, we will be there in 5 years. You will have arguments. Well, that's what the AI says. And you'd be like, yeah, but reasons. And they'll be like, that's what the AI said. I'm sorry, man. Like that is your future and my future too. Right? Because we're already totally there with government bureaucracy, right? You're like, yeah, but your regulation doesn't make any sense in my context. Do they care? No, they do not care. Because we're all just cogs in a machine. No one takes responsibility for their own place all too often. Anyway, the string performs a small transverse motion in the vertical plane, thus particle moves strictly vertically. So he's saying there's a plane of motion. All right, we can think about it 2-dimensionally. All right. He says let T1 and T2 be the tension at the endpoints P and Q. That's the portion of string. Since there is no horizontal motion, the horizontal components are constant. In other words, T1 cosine is equal to T2 cosine beta, right? So the horizontal force on that segment has to be constant. The vertical, we have two forces, and of course we have minus T1 sine alpha and T2 sine beta. If you go back to the previous page, those are just obvious, right? That's simple physics 231 stuff, right? Break into components. This is the horizontal, cosine for horizontals, sine for vertical, and of course this one's up, but that one's down. That's why the minus and the 1, right? All right, great. So we apply the Newton's second law to get the sum of the two forces, and the mass on that little stretch of string would be the density rho times change in x. It's a linear density. And so the x acceleration would also be calculated by the second partial derivative of y with respect to t. That's acceleration of the string, right? So getting to the point here, the sum of the forces is equal to ma, but the horizontal forces are 0. So that's kind of not interesting. Vertical forces, we're interested. And so we have the second partial derivative, the vertical acceleration times the mass, right, is equal to the difference in these tensions. All right. So then, this is the kind of tricky part. If you take the quotient of T2 sine beta and T2 cosine beta, and this and that, this is like the slope. Well, that's the difference of the tangents. That's just a definition of tangent, I suppose. Nothing much there. But there's something sneaky that's coming up. So he says the tangent alpha is the slope of the string at the point x, and tangent beta is the slope of the string at x plus delta x, right? So you're looking at a difference in slopes from one point to the next. And when you take a difference of slopes, then you've got a second difference, right? So you see where this is going to give us, as delta x goes to 0, this is going to become the partial derivative with respect to x of the partial derivative with respect to x, which we call partial squared x, partial y, partial x squared. And there you go. That's the wave equation. That's why we expect waves on a string to satisfy the wave equation. So it's not too hard, right? As if I was really mean, I would cover this more seriously and then every so often ask it on a test. No one wants to grade that though. No one. I know I don't. Yeah.
Is that an X in the box answer?
Yeah, that's an X. Wait a minute, no, that's a T. Yeah, this is a T because it's the time derivative here. So dimensionally, you can understand this. C is a velocity, so it's like meters squared over seconds squared, and there's a division by meters squared here. So the meters squared, it leaves you basically the net is meters over seconds squared. Over here, you got meters over seconds squared, so that has to be time.
Can you solve that for a function of y?
Can you solve?
To get a function y of x and t,
Yeah.
which was the original.
I mean, we can find y as a function of x and t if we have, boundary conditions that are appropriate. I think we usually, as we talked about, we have to have initial position and initial velocity, and yeah, we can do it. Anyway, any questions? I was going to give you guys the rest of the class just to talk amongst yourselves about the next one, and so I'll give you that time, and I also give you all of Wednesday. You have all of Wednesday to work on the boss fight. I don't really have much more, I think. Before I get carried away here, I should double check our schedule, make sure I'm not forgetting something stupid, right? Let's see here. Do we have, I'm trying to remember, we don't have a quiz or anything in here, do we? So we're just, I've covered Fourier series and solutions of PDEs already. So the material that I have scheduled for this week, we've already covered. So pretty much the next thing that happens is I collect boss fight 2 Friday. So
And the same bonus project.
in the same, oh, I guess that's the issue for Wednesday is so if you guys don't mind coming to my office and dropping them off Wednesday. I mean, you can just put them, if it's more convenient for you to put them here, I can collect them here. It's all the same to me. But
I'll give them to you now. It's not too much of
how about this? As long as we're all here, why don't we spend like the last, what's that? Oh, you want to give it to me now? If you're done with it, it's fine. You can give it to me now. I'm probably going to lose it. I'm just joking. I won't lose it. If I lose it, you get full credit, right? So there's that. But we do have, what, 20 minutes? That seems like enough time to review for the final, right? Do you guys want to look at an old final?
Yep. Yes. Let's go.
Let's
Would
go.
you provide me with an old final?
Just give us the problems on the final ahead of time, and then we can like study them.
This is not an engineering class, guys. Oh, that's right.
That's very fair.
I said it. That's right. I said it. You know, when I took circuits, I had to do 4x4s by hand. You guys did 2x2s. Whatever, dudes. Whatever. 2x2s. Seriously? Mm-mm. Mm-mm-mm-mm-mm.
Using a basket.
For shame. No, I used a TI-89. Let's see here. Actually, I think we had to do it by hand. Let's see, where are we? Differential equations, right? I mean, if you guys have questions about the boss fight, but I think you guys will figure that out. Let's see here. Let's pick a year. What year do you guys want?
Bring 25.
I haven't written it for this semester. Come on. Seriously? I always...
All 24.
Fall 24. All right, let's see if I can... Do I have... Here, we'll look at the ice is essentially a final.
There's an ice for this,
There used to be.
but it's not available anymore?
No. Because ice exams are now online.
Really? How does that work?
It doesn't work. That's why there isn't one.
Ah,
I tried very hard to keep there being one.
so there are no ices available in person anymore. That's just not a thing.
No, because the university made them all electronic. And so any department which allows one to be electronic
Yeah.
is being very foolish because they're not... Well, where do you take your electronic institutional credit by examination exam?
Surely in the testing center.
No, because it has to be the same for the online people.
Is it recorded?
No. So you see the problem and why they no longer exist for us.
This sounds like something we could take advantage
I'm very sad because I, had about 25 of them in the last decade. It's been extremely useful, but I could not convince them to bend to our main requirements, which are proctoring. So no one seems to care about that. Anyway, do you guys want to look at the version with the, let's look at the one with the answers, right? That's what you guys want to see.
Yeah, we'll work backwards.
I mean, I will post a blank one. You'll forget these answers, right? So actually, let's look at the one without the answers. That would be probably more useful, right? Otherwise, you guys won't get any kind of read on, All right. Yeah, sadly, it no longer exists, which is why it's fine to look at it, right? So how would you solve the first one? That is not separation of variables. No.
Substitution of something.
It is not that either. This is it has the form dy dx plus a function times y equals to q. This is a linear first order differential equation. Integrating factor technique is the way that's solved, which is what I was looking at over here, if I can find it. So I could talk about that ICE exam issue for like about another 20 minutes if you want to talk, but
I do, I want to hear about that.
I have a lengthy rant. Anyway, but it's kind of pointless, as most rants are. So we calculate the integrating factor, which in this case is x cubed, multiply by x cubed, reverse product rule, integrate both sides, answer. Yeah. What do you guys think about the second one? This one here.
Is that the exact equation?
That is an exact equation, right? You can integrate, if you just look at this thing, it's the differential of x squared y squared plus cosine y. So x squared y squared plus cosine y equal to a constant is the solution. All right. Keep in mind, the answer is not, so here's the thing, I warn, but it's like a self-fulfilling prophecy that you guys are going to do it. But like, put a box around this, I will take points off because that is not the answer. The solution is the level set. It's the collection of all points that set that equal to a constant, right? F equals to that, that's great, you've understood something, but that's not the final product. We're looking for a solution. All right, anyway. This is, of course, an implicit solution. Explicit is when I solve for y, like the boxed equation right there. Next problem. Vector field minus yx, find the Cartesian equation for the integral curve. So this is the one where we solved like dy dx equals to q over p, I think, for the vector field pq. So we do that. I think about the, like this, this would be the sort of basic integral curve equations, and then I think about, well, if I cancel the dt's, it just leaves me with, you know, in this case, x over y. I think the answers are circles. Yeah. All right, let's move on here. Next one, oopsies. Now this, and so the rules of the game don't change for the final, right? Like on test 1, I told you, I won't ask you to do a substitution problem where I just say, solve, right? That's not part of what I expect you to learn. I tell you the substitution, right? You can imagine a more evil form of myself where that was another thing I put on your plate, right? Figure out the substitution. That would open up a whole other, multiple cans of worms. It would be a lot of fun. Maybe in the future we'll do that. But, I mean, you guys should always, as all students say, yes, you should do that next time, right? Right, but this is just a substitution which is given, so you got to do the usual thing, which is to differentiate the substitution, meaningfully replace the expression and also the derivative with the new variables, right? And this one is hideous. Oh, yeah. I feel like I must have made a typo in writing this one out. Golly, this one's awful. This would be horrible to grade. Anyway, but there it is, as I said. Yep. Orthogonal trajectories, what do? It is terrible, I agree. So to find the orthogonal trajectory to this one, we need to solve the negative reciprocal slope, right? So we're going to be solving dy dx equals to like 1 plus sine x over minus y. Solving that related differential equation gives us the orthogonal trajectories. I also have a point, so we're going to have to fit the point to the data, right? And I like to test and see if students understand that they can't put plus and minus into the solution. When they need a minus, they have to put the minus, and I always test on this. I mean, I've tested on this issue of minus in like every first test in here I've offered for like years and years and years, and it's always the case that 40% of the students get it wrong. Sorry to be stereotypical, but that's how reality is. It's annoying, but you know, I didn't make up the reality. Take it up with the person who made it up. So I would recommend not doing that though. Not your place or mine. So minus 2c is 47 as it happens. And see, I don't need to solve for c. Why not just solve for minus 2c? Because minus 2c is what's in the answer anyway. So if I find that, I've got the answer. So put that up in here, then I've got, of course I need to choose the minus. So hopefully I have the answer down here. Yeah, all right. Let's move on. Oh, oopsies. Oh man, All right. So this stuff, I hope, after the dust settles and you go back to it, like, this stuff is really easy. We should never have lost points on this, right? And if you have, why was it? Probably it was algebra, right? So you need to, like, be careful about the algebra. And there are ways to do that, right? I big fan of course, completing the square, but that's, I think the first one just factors. That's like lambda plus 1 times lambda plus 2. This one's lambda minus 2 squared. This thing is d plus 7 times d minus 7, and this thing is like d minus 3 squared plus 4, so that's an irreducible. All right, let's look at the answers. So, of course, if we've got distinct roots, we just have exponentials. If we have a repeated root, we have to multiply by x. You guys know the drill. That one is, 3 plus or minus 2i, which gives us the exponential sine cosine solutions. And, of course, you could either go with your e to the minus 7x, e to the 7x, or you could alternatively, and, if you really wanted to be like one of the cool kids, you would go with cosh and sinh of 7x, because those are just, I don't know, it just looks better, right? Who wants exponentials when you can have cosh and sinh? I hope you've started to appreciate why those are important with your study of boundary value problems. Like the cosh and sinh make certain things much easier to see. However, sometimes there are other problems where exponentials just, you can't hit your whatever to either. You got to be open to both the exponentials and the cosh solutions for best results, I think. Okay, so here, this is a setup, but do not find the particular solution. So I'm using the annihilator method, right? So I find the thing that kills off the inhomogeneous term, which in this case is g. D cubed times d minus 1 is the thing. The d cubed kills off the x squared. The d minus 1 kills off the e to the x, right? And then the whole point of doing this is that then you can see that the d minus 1 that's implicit in the differential equations operator itself, which I called L to start with, right? It overlaps, which then means that you end up with like e to the x e to the x, right? So now you got to recognize these are the homogeneous terms, so those we don't want those, right? No homo, and we want the no homo, which is this piece and that piece, right? So here's your particular solution, and of course that's as far as you go, right? Read instructions. If it says just set up, that means that you just set it up. You don't have to then figure out the values of A, B, C, and D, which would take a chunk of the time that you should be spending on a different problem, right? This one here, cosine x, sine 2x. So I want a d squared plus 1 to kill off this, a d squared plus 4 to kill off that. And of course, over here I've got d squared plus 4, so the d squared plus 4 overlaps. And so the particular solution is going to have sine and cosine, but also x cosine and x sine 2x. So there's my particular solution, looks like that. Yeah. So you guys are allowed a page of notes, right? Front and back for the final. And of course, you do need to have all your Laplace transforming stuff on there. But certainly there's more than enough room for token examples of particular solution annihilators. That's, like you don't have to come into it just off memory, Okay, now this one actually is solved, right? So this one we need to be careful to actually work it through and not leave A and B in the answer, right? Because we're not done. So here the particular solution is ax plus b. There's no overlap clearly. So yp prime prime is just 0, which gives us the kind of funny algebra of yp1 equals to 3x1. So like this one's very dumb in terms of finding the particular solution. It just kind of like falls in your lap after you just plug it in. And so then general solution, of course, is homogeneous plus particular. There you go. All right. Let's see here. Isn't that the problem we just solved? Oh, I guess I don't know how to scroll. Sorry, guys. So here's This is like a trifecta. First problem we just solved. Second problem, there's an overlap. You gotta do some algebra. You guys have had a problem like this on your test, I think. Certainly in homework or quiz somewhere. You've seen this problem, something like this. I worked it in class, I'm sure. Something like it where we had overlap with the sign. And okay, and then this is the third, the follow-up to the previous two. I've got, you know, that's twice the previous problem, and this is 20 times the problem above. So that's why, or wait a minute, 10 times the problem above, I guess, because the previous problem had 2 sine x. So I need 10 times the homogeneous, 10 times the particular solution from the previous problem and twice the particular solution from the problem before the problem. And so that's by the method of superposition. Yeah.
Say for instance, you use this as a final and you have problems that are connected to each other. If we get the previous problems wrong, will you take off additional points for a improper plugging in of the answer?
It depends. It depends on how wrong the previous problems were. If they're within the realm of, I can understand that you were wrong but didn't see it, fine. I mean, if it's just so blatantly wrong that in the thing you use it, it's still like blatantly wrong. I mean, something like, it's hard to give an example in here of that kind of phenomena, but in like Calc 3, it might be something like you leave the answer as a scalar where the answer is supposed to be a vector, you know, something like that. But I usually do give partial credit if you look back, you know, if you've got the right. I don't usually take points off the superposition problem. I try to take points off the previous 2 problems where it's wrong, you know, because the point of the superposition problem is just to test on superposition. It's not to test on those previous 2 problems. That's, yeah. Oh, this one here, we were just talking about this, right? So notice here that the solution is centered at 2. So we need to kind of understand that, right? That formula means it's centered at 2. So I need to think about relative to 2 where are the closest singular points. This one just has 2, well, wait a minute, it has a singular point at 0 and also at, you know, 1 plus or minus I. And so the closest, so then I have to think about it in the complex plane. 1 over and 1 up, that's the square root of 2 from that. So I go 2 minus the square root of 2, 2 plus the square root of 2. That's my largest open interval of convergence by the convergence, the domain theorem. Here's a Cauchy-Euler problem. As you know, we're interested in real solutions in here, right? So it's great that we found, you know, a complex solution. X to the minus 2 plus I is an intermediate step, but the answer must be in terms of real quantities, yeah? So notice there's no I down here, yeah? So that's Cauchy-Euler problem. Of course, there's like there's 2 other cases for the Cauchy-Euler, right? Either have distinct roots, or you've got a repeated root, or you've got a complex root for the second order case, right? You're like, what about third order Cauchy-Euler, right? What about those on the final? The answer is no. I don't ask about third order Cauchy-Euler on the final because I didn't ask you about it up to this point either, did I? Did I? Why am I not doing that? We should do that. Or fourth order Cauchy-Euler. I mean, you can do these things, but they're not, like the applications where Cauchy-Euler comes up, they're quadratic, as far as I know. I mean, I showed you guys the wave equation. When you go to polar coordinates, Laplace's equation becomes Cauchy-Euler in the radial component. This one here, you can just integrate both sides. So like you don't actually need the whole technique that we used. This one, there's a trick. You could just integrate. So we're back to Calc 2 here. Still a thing. And to find the power series for e to the x squared plus 1, we simply do e to the 1 times e to the x squared to make a substitution into the Maclaurin series, right? So if you're not clear on your calculus 2 power series, you should review those at least a little bit. And again, that's something where having a sheet of notes should be super helpful to you because it doesn't take up too much space to have, right, your formulas for the exponential, sine, cosine, cosh, sinh, geometric series, maybe an example or 2 of that. That would be what I would do. Because that's what if you look at the totality of the things I've posted, that's pretty much always what I test on. It's either geometric series, an integral or a derivative of a geometric series times something, a sine or a cosine or a cosh or a sinh or an exponential sometimes like a substitution. But that's, you know, power series solution. Let's see here. System, right? This one has got what? Distinct eigenvalues, so we get linearly independent eigenvectors. Our general solution is the eigensolution, yay. This one here is what's called a nilpotent matrix. So like the cube is 0, which means we can just go to the matrix exponential and straight calculate the fundamental solution matrix. And then once we have that, we can write down the solution as linear combination of the columns of the fundamental solution matrix. There's your answer. Inverse Laplace transform. So you got to do the partial fractions on this thing. Yep. And then inverse transform. Let's see here. And then what's next? Laplace transform the differential equation. Solve for big Y. Again, you got to do inverse Laplace transform. And yeah. Let's see here. This one, obviously not Laplace transform, right? Because, yeah.
Oh, sorry. Do we get the Laplace transform sheet as well
That's
back in front?
no. That's you bring the Laplace transform sheet with notes on it. Yeah.
Okay.
So you can use my sheet. You can you know, if you want to put everything in size 4 font and bring a magnifying glass on whatever. It's all good. Just only 2 sides of the paper, right? So, yeah. And so this one's variation of parameters, right? Because we can't solve this with undetermined coefficients because secant is not a product or sum or solution, product and sum of like homogeneous solutions. So we gotta use variation of parameters for that one. This here is a bonus question, and all of my previous comments about I won't test on substitution and all those things I say that I won't do, those are all off. Like in the bonus question, I am allowed to do whatever I want. So I could ask you a completely new thing and violate the terms and conditions of the guardrails I put on the test in the bonus question. Are we understood? But there may not be a bonus question either because I don't know. Every so often somebody solved this thing. But this is actually a problem which led, I don't know if I showed you guys that paper I wrote with my brother or not, but like this problem kind of led to that paper. But this is really, really weird. Look at the solution to this thing. C1 e to the minus e to the minus t. We never saw anything like that, right? But anyway, this is pretty good representation of possibly your final, but I do think that like the separation of variables thing and just the plain boundary value problems make reasonable final exam questions. Like not the Fourier calculation, obviously, but setting up the general solution, those are not unreasonable.